Hi, guys. So today we're going to talk a little bit about a connection between quantum computers and high energy physics. So when you think of high energy physics, I'm sure you think of things like particle accelerators, all these big experiments that they're doing. Here's the Super Kamiokande in Japan, the muon experiment that they're doing at Fermilab recently. But if you are like a theorist and you want to calculate things about various particle physics problems, what you typically do are these so-called lattice gauge theory simulations, and you run them on the biggest supercomputers in the world. There's a kind of a development in the last 5 years where people are thinking maybe you can use quantum computers to actually speed up this process of simulating these types of problems. So this is a paper from the Zoller and Black group. And here they were simulating the real-time dynamics of lattice gauge theories. I think they did so-called Schwinger model. And so they did this in a 4-qubit ion trap machine. Maybe this one is a little bit more recent. So this one, it's not in the title, but this is one of these hybrid quantum classical algorithms where they do a quantum simulation of again, this kind of lattice gauge theory. So I have a bit of a connection with this story because actually this topic is kind of what I did in my PhD. So this is my PhD thesis. And so you can see that the title is Density Matrix Renormalization Group, New Approach to Lattice Gauge Theory. So this is back in 2003. So I just finished my PhD in Australia and then I moved to Japan. And because I did this kind of topic, when I was working newly with my new boss at the time, Yoshi Yamamoto, he told me that a good topic that I should be working on is quantum simulation. And so quantum simulation was some kind of new buzzword that was going around the time, around 2004 or so. Actually, in hindsight, I completely misunderstood him because when he was saying I should do quantum simulation, he had in mind a kind of a totally different type of quantum simulation. But he was away in Stanford for about 9 months of the year. And so in the meantime, I just went and wrote this paper, which at the time was kind of pretty esoteric. I remember him scribbling the corrections of this paper. Do you want to submit this to PRA or even a more specialized journal? Because he thought it was kind of technical. But actually, in hindsight, a lot of people are working on this now. So I'm going to talk to you a little bit about how you simulate these kinds of things on a quantum computer. All right. So what is quantum simulation? Basically, the idea is that you have some physical system, say on the left here, that you want to understand. And the idea of quantum simulation is that on the right, you have some more controllable quantum system, which you can tune so that it kind of mimics the same dynamics of the system that you want to study, right? So the thing on the right could be anything from a fully fledged quantum computer or something actually a bit simpler that you can control well enough so that it still mimics the same dynamics, right? This kind of idea is actually the origins of quantum computing itself because Feynman said back in 1982 that you actually can't simulate these quantum many-body problems because basically it's got too many variables. So the number of variables keep on growing exponentially with the system size. This is what makes it really hard to simulate these systems. So just to give you an idea of a prototype system. So for example, here's a spin chain. If you want to understand anything about the system, one of the things that you often have to do is to diagonalize this Hamiltonian. So in the bottom right here, I've got the Hamiltonian that you might need to diagonalize. So for a 2-spin system, it's only 4x4, but if you have a lot of spins, then it gets very big very quickly. Even for something so this is, I think, the biggest quantum computer. I keep on saying quantum computer. I'm so used to saying quantum computer, right? Even for the largest supercomputer in the world, it currently can process 400 petaflops. So that's peta is, what is peta? 10 to the 15? No, 10 to the 15. Yeah, 10 to the 15. Yeah. 10 to the 15 floating point operations per second, right? So even for this kind of massive scale machine, for something with like 60 sites, the number of numbers in the wave function is already 10 to the 18. So, that's just to go through all the numbers once. Obviously, in a calculation, you do need to do that many times. So obviously you're going to hit a wall, and this is only for 60 spins, which is really nothing compared to some, crystal, which might have, Avogadro number of spins. Right? Feynman's idea, so this was actually like a conjecture, right? So that just means Feynman guessed the answer, right? And it was proven to be true only in 1996. This is Seth Lloyd's paper. It's a one-sentence abstract. So basically, he just says Feynman's 1980 conjecture is shown to be correct. Basically, what he did in this paper was pretty simple argument. What he said was that, well, say you want to perform like the time evolution of some Hamiltonian, and let's say it's this spin chain model, just for argument's sake. And so the spin chain model only has n order of terms. So if it's got like n spins in it, then the Hamiltonian itself only contains n terms, right? So if you want to perform a time evolution, then what you could do is to do like this Trotter decomposition of the Hamiltonian. Here you've got the e to the I ht, and then if you substitute the Hamiltonian that you're looking at, you can approximate this with roughly order n operations. And if you view each of those e's inside the brackets there as a gate, then basically you can simulate at least one time step forward, only scaling with the number of sites. Remember, in the computer simulation, in order to do this, you needed 2 to the n. So this is like basically n gates versus 2 to the n gates.
Can we really do this with quantum supremacy?
What? What?
Boson sampling. Can we really do this with boson?
Can we do this with boson sampling?
Or fermion sampling? Or do we have anything called fermion sampling?
Fermion sampling. Well, you're confusing me with the question. Yeah, I think you're doing it on purpose. But I mean, boson samplers can't do any calculation, right? I mean, so you could do this on some quantum. You need a quantum computer to do this.
So it's not a quantum computer?
What? Oh, the boson sampler?
Yeah.
No.
Really?
Wait a minute. Going back to my sort of story. So in 2004 or 5, this was just an emerging idea where it seemed to be sort of just about technologically possible around about that time. And most people were looking at things like solid state physics applications. But in terms of saying that high energy physics could be simulated on quantum computers, I think our paper was actually the first one. So there's kind of 2 types of quantum simulation. So if we go back to what I was saying, where my supervisor at the time, he had a different idea of quantum simulation to what I was thinking. He was thinking of more of this sort of analog type simulation. And what that basically means is that you have some quantum device which is fairly limited in its controllability. So you don't have a full quantum computer, but you have something which is just controllable enough so that you could simulate some kind of physical system. So that's the thing on the right, where you basically don't have a full quantum computer, but you can just tweak it enough so that you can still simulate it. But what I did with that high energy physics paper was to say that, well, actually, suppose we have a quantum computer, how could we simulate things like lattice gauge theories, high energy physics problem, using that? So it's, these are related approaches, but sort of the philosophy was a little bit different. And, back in sort of 2004, the one on the left seemed much, much more feasible than the one on the right. But if we zoom forward to 2021, actually quantum computers are actually starting to emerge. I mean, this basically explains why people are now much more interested in doing this kind of digital type of quantum simulation. So how do you perform time evolution? The simplest kind of way is actually, again, to use this Trotter decomposition. So it's the same thing that I mentioned with Seth Lloyd's paper. And so the simplest kind of quantum simulation that you can do is you say, okay, I'm going to start with some initial state, and then I'm just going to evolve it forward in time. And classically, that's already a super hard problem. Doing that time dynamics is like even harder problem usually than finding the ground state or something like this. If you can construct such a unitary operations, you can then plug it into things like phase estimation and then extract energies if you like.
What kind of research you can do with that? I mean, to me, it seems like it's just simulating something that does nothing because you just simulate those fields. You know, it's like if you say simulating the solid state, so okay, you simulate a crystal, but it's a crystal, it just does nothing. It just stands there and...
Hold on. Okay, so even simulating a crystal, you think it's not simulating?
I mean, it is, but, you know, solid state is just solid.
Well, you cannot
maybe if if you apply voltage to it, you do some semiconductor simulation. You have something you observe there. But here I just don't see what you observe.
Right. Okay, You know, so when you look at a Hamiltonian, right, and then I mean, even in the stuff you're doing. Like you look at the Hamiltonian and then you diagonalize it. You look at the ground state, right?
Yeah.
And then in your case, you say, "Oh, there's Majoranas in the ground state."
Yeah.
Right? So finding that is already kind of a non-trivial thing. In your model, it's exactly solvable because it's simple enough. But in these models, you can't even write down what the ground state is. This is basically the difficult thing about particle physics, which is that, like, even, you know, I remember somebody saying, like, it's completely wrong, but they're saying, particle physics is easy because it's only particles, and it's like, it's not involving like many body. It doesn't involve like a complex many body process, right? But you know, that just shows that this person had no idea what they're talking about in particle physics. But it actually is a many body problem in particle physics because basically the ground, even like writing the ground state, which actually is something with like basically the vacuum, it has like no particle. Even nothing is like quite a complicated object to analyze. So let me just give you a kind of a taste of how it works to simulate high energy physics problems. A kind of a simple type of problem that people look at is quantum electrodynamics. You might have learned from electromagnetism that things like the electromagnetic field you can write in terms of these electromagnetic field tensors. So this F contains magnetic field, electric fields. And this part is basically like the Dirac equation, right? And then these are like the Dirac matrices, and this is like the vector potential. This is like the mass of the electrons and so forth. For example, in one dimension, which is this so-called Schwinger model, the 1D version of this kind of looks like this. So it's basically just like electrons and positrons just in a line. And then in one dimension, there's no magnetic field because for magnetic fields, you like need a curl. Like it's magnetic fields are like a curl of the vector potential, right? So one dimensions, magnetic fields don't even exist. Photons don't exist as a result. So basically all you have are like electric fields, right? So you have a bunch of electrons. And so the kind of degrees of freedom are like these electrons, positrons, and then the electric fields themselves are also like some quantum variables. So you can turn this into a lattice model. So this thing is like a continuous space model. And then you can turn this into like a lattice model where instead of the electrons being just like anywhere, they're just fixed on lattice sites. And then there's also electric fields, which are also some kind of variables. And the electric fields actually are also on the lattice like this. In the end, actually, what it boils down to is something pretty simple. If you just look at the electric field part of the Hamiltonian, what you get are just like, these are like diagonal terms. This is like the electric field squared. So you can imagine like on each link, there's just discrete values of the electric field, like 0, 1, 2, 3, or goes to minus. And then this would just be the square of the electric field. And then these are like some kind of hopping terms, which means like it changes the electric field, but then it changes it in this like square configuration. And so this Z here is like the product of 4 of these U's, and each U is something that like shifts the electric field by 1. This is the case for electrodynamics, but you can approach something like QCD, quantum chromodynamics, by essentially elaborating on the same idea. Basically, what happens, you can also map these types of operators. Essentially, it boils down to, again, a Hamiltonian that looks very similar. Again, this Z thing is some product of 4 U's, where each U is something that's like raising or lowering some registers. And for quantum chromodynamics, you need actually 8 registers per link. So it sounds like a lot, but I mean, that's what you need for complicated theory, such as quantum chromodynamics. Essentially, what we did was to basically map this whole kind of complicated particle physics problem onto some kind of Hamiltonian, which, okay, in terms of a spin model, has some very crazy interactions. However, at the end of the day, it's still just a spin model. And then once you boil it down to a spin model, you can just basically simulate it just using the same way. So that's basically what I did in this old paper.
Did you say that digital simulation becomes more popular?
I think so, yeah. I mean, basically, it's more feasible these days. And I think this distinction is now kind of blurring, right? Okay. So back in like 2005, there was a kind of a clear distinction because, so I didn't really talk about it, but there was this famous experiment where they made like an artificial Bose Hubbard model, right? And in this experiment, in this Bose Hubbard model experiment, they didn't really have any control over, like, say, individual atoms or anything like that. So they could just like make the potential, the interactions were naturally there. And so just by essentially, having it at the right temperature range, creating the right potential, this kind of model just sort of naturally formed, right? Yeah. That's quite different to something like a quantum computer where, you're applying individual gates. You need to control every qubit, really perfectly. But, actually we're sort of getting to that stage now where you can do such actual gates with, quite long circuits. And so it's kind of much more feasible today, right?
So what I like about the digital approach is, maybe I don't understand the analog approach too well, but to me it seems like, and that's also what we talked about yesterday, it seems like you're very limited to what you want to simulate. Like, for example, I imagine it would be hard to simulate like 3D interaction if you have only 2D topology in your analog quantum simulator. But if you have a digital one, you don't really care what is the topology of your processor, because you can apply swap gates and just reorder things and apply gates to it. So it seems like your processor, as long as you have all the gates, can just do anything, any system. Yes. But for the analog one, like, you can only do what you build.
That's right. Okay. Yeah. Well, that's completely right. Okay. But
I think the difference might be in the analog one. The system might be unique in the sense that you build it to do this, but the digital one might not be like that. I think it can do this and do that.
Yes. Yeah. So the quantum computers sort of can do anything, right?
Yeah.
In principle, yeah. Analog quantum simulator can only do the model that you are just making right now.
So for this lattice gauge theory simulation, so what is the limitation of that? So I know for the digital version of the simulation, it must be hard because you might require very long circuits to do that, and then your fidelity of the current quantum computers may not be able to actually accentuate that type of calculation. But for the analog one, is there any limitation? Because if it works so well, then why are high-energy physicists still calculating using these super primitive computers?
Well, I think because, for example, there's probably more advanced ways because our paper was the first one. So, but even in this, in the thing that we did, this kind of interaction is a really crazy looking interaction actually, right? This Z is like a product of 4 of these U's, right? And then each U contains operators act on like 3 registers. If you look at that as a spin interaction, that's a crazy spin interaction, right? Good luck modifying your, some whatever system you have to turn it into that, because you're going to have to do some crazy engineering to make it that, right? Analog simulation kind of works well when you already got a system that's more or less the thing that you're trying to investigate, right? This Bose Hubbard model experiment, this was a very natural kind of thing. Things like the interactions were already there. So this is when it works very well, right? But if it's like just too far, then I think it's just too hard to do it. And, yeah.
In the tritype decomposition in doing your digital simulation, how large or how small should that time really be for you to really be still doing something meaningful?
So, for example, in the phase estimation, so say you wanted to plug that U into that circuit, right? Then you have to perform this multiples of U, so U to the 2 or 4 to the 2j, right? U to the 2 to the j is basically means that your time evolution is quite long, right? And so if you want to do like a really long time evolution, then your the Trotter time that you're chopping it into will need to be like, quite accurate. Otherwise you're going to like deviate, and by the time you're simulating your long time evolution, you're going to get some nonsense if it's not small enough. So if you enjoyed the video, then please don't forget to subscribe to our channel. And so we will see you next time, another video like this. So bye.
Bye.
Bye.